Hello students of science. In this video we're going to talk about gas volumes and go over the ideal gas law. So first thing we need to understand is that the volumes of gaseous reactants and products are always going to be in ratios of small whole numbers. So no decimals here, no fractions or anything like that. So let's say we have the reaction of hydrogen gas burning with oxygen gas to make water vapor. So that's going to be H2 plus O2 makes H2O. And then you balance it out and we're going to have two hydrogen molecules that are going to react with one oxygen molecule to produce two molecules of water. So these are whole number ratios. That will come into play in just a moment there. If we were to do this as a volume of gas, we would say 2 liters of hydrogen is going to react with 1 liter of oxygen to make 2 liters of water. Again, these are going to be whole numbers, and usually they are going to be small things as well. If we were to look at a different gas, let's say methane and oxygen burns to make carbon dioxide and water, 1 molecule of methane, 2 molecules of oxygen is going to make 1 molecule of carbon dioxide and 2 molecules of water. Nothing really new here, but those ratios will come into play when we start doing some calculations with gas volumes. So Avogadro's law basically comes along to the idea that if you have the same volume of gases at the same temperature and pressure, they are going to contain the same number of molecules. Let's say I have 3 balloons. First one here is filled with helium, second one is going to be filled with ammonia, and then the last one is going to be filled with oxygen. Now, we will look and see at the bottom that these all have different masses. However, they all have the exact same number of molecules. 9 here, 9 there, 9 there. So they have the same temperature and pressure. They're going to have the same number of molecules. They are also going to take up the exact same volume. So standard temperature and pressure, if you recall, that is going to be 1 atmosphere of pressure and 0 degrees Celsius. 1 mole of hydrogen gas at standard temperature and pressure is going to have 6.022 times 10 to the 23rd hydrogen particles. So this is nothing new, we covered that before. And that's actually going to work out to be 22.4 liters exactly. If we were to look at a different one, like let's say 1 mole of oxygen, same temperature, same pressure, going to have the same number of particles, that's also going to take up the same amount of space, 22.4 liters. Carbon dioxide, same idea here. So it doesn't really matter what the gas is, at the same temperature and same pressure, they're going to have the same number of molecules, same number of particles there when we're talking about moles. So let's look, we have another example here, helium, nitrogen, and oxygen. They're going to take up the same volume at that same temperature and pressure. However, they are going to have different masses. Let's look at these 3 balloons here. Same volume, 22.4 liters, same pressure, 1 atmosphere, same temperature, same quantity. The only difference is going to be the neon is going to quote unquote weigh the most. It's going to be a little bit weird because of density, but neon is going to have 40 grams of mass, oxygen 32 grams of mass, and carbon dioxide 28 grams. So we have all these different gases here, nitrogen, oxygen, hydrogen, chlorine, and helium. If we were to put them all at the same pressure and the same temperature, they are all going to take up the exact same amount of space. 1 mole at standard temperature and pressure, 22.4 liters, that's pretty much a law. So let's talk about the ideal gas law and how this plays into it. The ideal gas law is going to add in numbers of moles of a substance to the pressure, volume, and temperature, if you recall from our combined gas law. Now we're going to add in moles of a substance. And the equation that you want to know is PV equals nRT, or PivNert, if you're not cool like me. But PV equals nRT. The new one in there is going to be R, more on that in a second, and N. N is going to be the number of moles of a substance. So you're going to want to write that out. P, pressure, V, volume, N, number of moles, so like 1 mole, 0.8 moles, something like that. R will be our constant, we'll get to that in a moment, and T is going to be the temperature in Kelvin. Very important, that needs to be in Kelvin. So a couple examples of how you can use PivNert, or the ideal gas law. You don't need to write these down. If you just increase the amount of substance, you will increase the volume. So here I have an uninflated balloon, here I have an inflated one. It seems kind of like a dumb thing to really think about, but why does the balloon blow up when you put air in it? Well, the volume is going to increase because you are increasing the number of molecules of air that you're putting in there. More air inside there, the balloon is going to expand. If I was to only increase the amount of a substance, that would also increase the pressure. So if we're saying a sealed container, if I put a lot more stuff in there, that's going to be higher pressure. That makes sense. More collisions going to happen with the walls. So R, as I mentioned, is our constant. That is going to be equal to 0.0821 liter atmospheres per mole Kelvin. You don't necessarily need to be able to rattle that off the top of your tongue. Why that's important though is if you're going to use R, and you're going to, all the units have to match. This means pressure will need to be in atmospheres, volume will need to be in liters, temperature will need to be in Kelvin, and the amount of substance will have to be in moles. If you don't have these things in those units, you have to convert them. Otherwise, R will not work and you'll have to use a different value. I will give you this value. If it's not in liters, make it liters. If it's not in atmospheres, make it, and so on and so forth. Everything needs to be converted to these to use R. Here we're going to look at the effect of pressure by changing temperature, volume, and number of gas. So here I have a particle hitting the different sides. Watch what happens when we increase the temperature. It's going to be moving faster, hitting the sides harder, and the pressure goes up. If you put more stuff in there, increase the number of particles, more collisions, higher pressure. If we decrease the volume, make it so that there's less space in there, you're going to have more collisions as well. All of those will increase the pressure on that. Finally, diffusion and effusion. As we've talked about before, and as you may have covered in biology, diffusion talks about how something is going to spread out and mix, even without stirring, high to low concentration without energy going in there. You can put food coloring in water and just let it sit. Eventually it will spread out evenly. You could also let some perfume out into a room and it's going to sort of stink up the whole place there, even without moving it around. Effusion, as I've mentioned before, gas particles can pass through a small opening. So here we have a container. When you open it up, those gas particles slowly start to move out and spread out through the air. Now, a rule of thumb, a smaller particle is going to effuse faster. The smaller it is, the faster it's going to be going, faster it's going to be diffusing and effusing. The rate of effusion can be compared to another gas's effusion rate, and you can get a pretty accurate, pretty rough, but accurate estimate of its molar mass. So here I have a container there. Some stuff is going to be going out. You will notice that the green is going out in greater numbers than the blue. That is because the smaller it is, the faster it goes out. You can use those rates and compare them and get a good idea for the different molecular mass of each one. So smaller particles going to effuse faster.